All right, so welcome back again. So this is lecture number 17. So in the last class we were discussed about the DC motor characteristics, DC motor characteristics, and in this class let us explore the application of the DC motors based on the type of motors and other characteristics, and also see some problems related to the all like up to the efficiency calculations, right? So here we seen based on the excitation the DC motors are of three types majorly. One is the shunt where the field winding is connected in parallel to the armature. So when it is connected in parallel to the armature, the important thing what we come across is that the amount of the current supplied by the source is equal to the armature current plus the field current. And also you can observe the other equation, the field current is equal to the applied voltage divided by the field winding resistance. Clear? So these things I already shown you. Once again, just let us have a review on these things. And one more important thing is that as because IF is V by RF, where V is constant and RF is constant, so thereby IF is constant. So it is a practical thing that we can assume the flux produced by this shunt field winding is constant. So thereby we can say the torque is proportional to IA directly, as usually torque is proportional to flux and current, product of flux and current, but as because flux is constant here, phi is constant here, so we can say torque is proportional to Ia. And one more important expression is that the speed of the machine is proportional to Eb by phi, or phi into n is what? Eb. So Eb by phi, so phi is constant, so I can say this as n is proportional to Eb. So these are the important equations which we come across in the previous characteristics. Now based on these characteristics, we can conclude that so the speed is approximately constant for a DC shunt machine, and the adjusting the speed medium starting torque can be obtained in these, like how much will be the starting torque, that depends on the armature current. Initially armature current is usually low, that means torque is low, but still it can produce the medium starting torque. So in these kind of applications, we use the DC shunt motor. What is the thing? First thing is that constant speed. Second thing is that medium starting torque. So wherever these requirements will come across, so we can use, so for example, some kind of, so like the constant speed drives in like all kind of things where you have the application of constant speed, so you can use it like lathe machines and centrifugal pumps, so where speed will be constant, some machining tools, mechanical machining tools, blowers, fans, and reciprocating pumps. So these are the certain applications where we can use the shunt machine. Similarly, the series machines, so try to observe. We observe that the armature current is equal to the source current is equal to the series current ISC. So in that case, so if we observe clearly, the flux is proportional to simply armature current. And as torque is proportional to phi into Ia basically, so when we substitute phi also as Ia, so torque is proportional to Ia square, the armature torque. Here also you can call armature torque. So this is one important conclusion where the torque is proportional to Ia square. So that means it has high starting torque. It has high starting torque. Why? Because it is Is square. So for example, if starting current is, let us say, 0.01 amp, or something like 1 ampere or 1.2 amperes, you can consider in that way. It is Is square, so that's why it is having higher starting torque. And we also seen one more thing, that so speed is proportional to 1 by Is square. speed is proportional to 1 by Ia square. So based on this, one thing we can consider, so as current varies, the speed is varying, so it is a variable speed applications. Okay, so that is one important characteristics of the DC series machine. So it is used mainly for variable speed applications. So where will be the variable speed applications? Like traction, like in trains. Sometimes I need low speed, sometimes I need high speed, and various examples are given: cranes, hoist, conveyor, and trolley, cars, etc. So in cars also we can use the series motors basically, and those must have the high starting torque. So wherever this I square I cube will be there, so that kind of expressions will have high starting torque in comparison to the previous. This is medium starting torque, Ta is proportional to Ia. So this one is, so Ta is proportional to Ia square, means high starting torque. So we had seen the other characteristics also. So you can see these will be the corresponding applications. Next is the cumulative compound, in which we said that the total flux is the sum of shunt field flux and the series field flux. If the series field flux adds to the shunt field, we call that as a cumulative. So this is like predominantly used. The differential compound is less used. So when this is opposing, the series field flux is opposing the shunt field flux, this becomes the differential compound, whereas this becomes the cumulative compound. So it is also used in variable speed applications and varying speed and high torque applications. So this also used in high torque applications. Why? Because wherever you see series winding, so you try to expect that a high torque can be produced. That is one important thing. And these are the various applications. So these are important for competitive exams. Usually they will give some kind of things like that. So in cars application, what kind of machines are used? Is it DC shunt motor, DC series motor, or cumulative? So in car you should interpret yourself, I need a variable speed and high starting torque. These are the important. Starting torque should be high and variable speed is achieved. In which we achieve this series motor. So like that, so some questions will be there. Let us say some a constant speed applications like fan. So fan need to be rotated constantly. So some blower or some centrifugal pump like the for pumping the water. So there, so a constant speed is required. A medium starting torque is enough. So you will not have a high starting torque requirement in this. So you can use in that application this shunt motor. Okay, so in that way, so these are important for competitive exam, especially Genco, Transco. They'll ask these things. You refer back previous papers, you will come to know that. See, so like for icing machines, for printing press, or for air compressors, what kind of machines are going to be used? So like cumulative compounds. So these things you have to get clear awareness very carefully. Okay, so here just high starting torque and variable speed. So this is the application, variable speed and high starting torque. But you have to look for what kind of applications is this. So like that, so try to get awareness on all these machines. If somebody want, so if you don't know what is like trolley, or let us say some, let us say locomotive, just you type in Google, you'll try to get its picture and try to analyze yourself. So and try to interpret yourself what kind of machine I am using in there. Okay, and after seeing these characteristics, this we already seen for the generator, but in reverse way. So just let me tell you the power stages in a machine or motor. Power stages in motor. Motor. We said that motor input is electrical, so which is equal to V into I. The applied voltage is V and the current is I. So immediately the electrical losses takes place, which is equal to copper losses Ia square into Ra and Ish square into Rsh, or If square into Rf square. It's in general. And left out power, once I'll subtract these copper losses from the input, the left out power is what the power developed in the armature. So this we call as usually as PA. PA is equal to EB into IA. And here with the help of this power we could able to produce the armature torque. This can also be called as a gross torque developed by the armature. Gross torque developed developed by armature. I said just a simple expression many times that the torque is corresponding power divided by the angular velocity. Remember that. So this can also be further written as Pa divided by omega can be written as 2 pi small n, or so Pa divided by 2 pi capital N by 60, where small n is RPS, capital N is RPM. This also we said several times. Next is, so if we subtract the constant losses from this armature power, then the left out power is what? The mechanical power available at the shaft. This is available at the shaft. At the shaft. So the amount of the power available at the shaft we call as net amount of the power. So the torque available here we call as shaft torque, and this power can also be called as, or this can also be called as net power or power output, or power output. So the shaft torque can be obtained as net power or power output divided by the speed. The speed of the armature is equal to speed of the shaft, so I can use same speed. So this I can write as P out divided by 2 pi n, or P out divided by 2 pi capital N by 60. So these are the power stages. Just try to interpret yourself and try to get. And we seen previously like the commercial efficiency, electrical efficiency, mechanical efficiency. So once you get these things, the efficiency is overall efficiency, which is commercial efficiency. So I can write as P out divided by P in. So P out is what? The mechanical power, motor output power. So divided by P in is what? The input power. So this gives the efficiency. And just let me write what is the mechanical power. P mechanical power or P output power is equal to, can I write in this way? So input minus P in minus all losses. Let me see what are the different losses here. One is here minus, this one is minus, P in minus copper losses. So depends on the type of machine, whether it is series machine or shunt machine. Let us say in this way. So field losses will be there, that is what? IF square into RF. If it is a compound, you will have shunt and series, both currents, both field losses. Okay, you try to interpret. If it is shunt, IF will become ISH. If it is series, IF will become ISC, like that. Okay. So next is the iron and friction losses. So iron and friction losses, and just prior to that, just here one more thing is there. Here there will be brush arrangement in the armature, so that armature brush contact may have resistance. So here let me write as power loss in brush contact. Brush contact, if brush contact has some resistance, thereby some voltage drop is there for brush. Usually that is equal to, if brush voltage for both brushes is given, that is brush voltage into armature current is what? The power usually. So this VB is for two brushes, remember that. If per brush is given, 2 into VB, like that. So this is brush voltage drop, two brushes joint, like, so two brushes will be there for a machine. So that power minus the iron and friction losses. Iron and friction losses. Iron and friction losses. This we call usually as stray losses. Stray losses. So if we subtract all these things, so what we get is what? The output power. So that output power divided by input is what? The efficiency. Clear? So now, so based on these all kind of analysis, let us have a simple problem. So see here, so one example problem. So it is a 4-pole machine. So let me put the every given data over here. So the number of poles is P is equal to 4. So the voltage is given, which we consider for a motor, usually this notation, V is the input voltage, which is equal to 240 volts. So what kind of connection is that? Winding connection, wave connection. So remember, this is the first problem on the wave connection, wave connected waveform or wave connected winding. So remember, in wave connection, the number of parallel paths, what is A? A is the number of parallel paths, number of parallel paths. So the number of parallel paths for a wave connection is always 2, is always 2. So number 2. So this you have to remember. So I had not gone in detailed wave connection, but just the conclusion point from the wave connection is that the number of parallel paths is always 2. This is always 2. So if it is lap connected, if it is lap connected waveform or lap connected winding, for lap connected winding armature, the number of parallel paths is equal to number of poles. This we discussed several times. But for as wave connected, so the number of parallel paths are always 2. Remember this. Okay. So next, what else is given? It is connected in shunt. So shunt motor. So once you see this, so let me quickly draw that shunt motor diagram so that it is easy to understand rest of the things. So this is the brushes, this is the armature, and armature has its armature resistance usually, and I will have a field winding. How this field winding is connected? In parallel to this armature. So let me connect this in parallel to this armature, and it has some shunt field winding resistance. The current through this is what? ISH. This armature current is what? IA, and this will have some back EMF, as because it is motor, so I'll call as EB. If it is generator, I would have shown as EG. So this entire thing is going to be connected with a source of V, voltage V, by a battery kind of thing. And so when this is connected with a voltage V, it is going to supply a current of I. Once you see shunt motor, just draw this diagram immediately. Then with this you will get some information, right? Next is, so it gives means this motor output is the rotational in nature, means this motor output is what? The shaft power. This is the shaft, let us say. So where we may use some mechanical device here, and this shaft power is what? The P out, P out. So output power is given. How much is that? 11.19 kilowatt. So let me write P out is equal to 11.19 kilowatt. And at what speed it is this? So at when speed of this machine is, like, let us say if this machine is rotating at a velocity of n, or angular velocity of omega, so at this speed the output power is 11.19. This is what, whenever they say output, it is final output, that is what we call net output, which we call this as mechanical output power. So how much is the speed of this? Speed is 1000. Speed is 1000 rpm. 1000 rpm, revolutions per minute. That's why I used capital letter N. If it is given as rps, I will use small letter n. Okay. So next is, so what else is given? Let us see. Running this and drawing armature current and field current 50 and 1 ampere respectively. So let me write there itself. So IA is equal to 50 amperes, and IF is equal to ISH, which is the shunt field winding, is equal to 1 ampere. So you can write here also, no issue. So IA and ISH is given. Once IA ISH is given, we can say I. So there itself, or let me say later on. So I'll find that later on. So next is, yeah. So or whatever information I could conclude, let me conclude there itself. Once this is given, so the I is equal to IA plus IF just by looking at the diagram. Okay. So this is 51 amperes. That is 50 plus 1. Okay. So right, this we may utilize for later on, just that's why I am immediately concluding from the diagram. What else is given? Right, so it has means armature has 540 conductors. We said that several times. The total number of conductors is represented by the letter Z, so the total number of conductors is equal to 540. What else is given? Its resistance is also given, see here. So see, its resistance means which resistance? Armature resistance. Usually the field resistance of shunt connected motor will not be this much small. If it is this much small, it will have a huge current in the field winding. Huge losses takes place there itself. So this is the field winding. This is the armature winding resistance. Ra is equal to 0.1 ohm. Next, what else is given? See that. What else is given? Assuming a drop of 1 volt per brush. 1 volt per brush. That means per brush voltage drop is 1. So this is one brush. Here 1 volt. Here another 1 volt. Here another 1 volt. So these are what? Voltage drops across the brush. Brush drop. Brush drop. This also brush drop. Now total brush drop, let me consider as total voltage drop across across two brushes. Two brushes. In a DC machine usually we have two brushes. So that let me call as VB is equal to 2 into 1 volt per brush. So which is equal to 2 volts. Okay. So what else is there? Next. Right. So find the total torque, useful torque, and useful flux per pole, rotational losses, efficiency. So these we need to find. So the total torque means torque developed by the armature. This is what TA. The useful torque means the final or net torque, which is equal to TSH, shaft torque. So the flux means phi, and the rotational losses means the, let me say here, what is the rotational losses is this entire thing will be treated as a rotational losses, usually iron losses, and these may be negligible. So under such circumstance, can I say output minus this armature power is what? The losses. So let me write that. So B minus C, this losses is equal to B minus C. What is B is armature power. What is C is the mechanical output power. So difference between is what? The rotational losses. And what is the efficiency? Efficiency is equal to C by A, final output by input. So P out by P in. So these we need to calculate. So once you have the equivalent circuit, it is easy to have all these kind of analysis. So that's why, so better to draw the equivalent circuit immediately when you see the given data. This all are about the question. Just I try to analyze the given question along with this diagram. Now think of what can we do to solve these things. So let us take part A. So what is part A? Part A is to calculate the armature torque. So how much is the armature torque? We had seen previously. Armature power divided by the angular speed. So speed, is it given in RPS or RPM? You see that. So this, so or let me write this as, so armature power can I write as EB into IA divided by, so omega as 2 pi n by 60. Why? Because n is in rpm, so I am choosing capital N, so divided by 60 will come. This is the ultimate expression. Now in this expression what I need? EB I need. So how can I write EB? So again see the diagram, so this is what the EB. So this voltage, applied voltage, minus IARA, that is the armature resistive drop, minus brush drop is what? The EB. Just see that previously also we said you subtract all the losses or voltage drops, then left out voltage is what the EB for a motor, or you can say V is equal to, so this entire EB plus armature resistive voltage drop plus brush contact drop. So in either way you can write. So let me write EB is equal to V minus IARA minus voltage drop across 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 brushes. Usually this brush contact drop is negligible, so you can consider 0 if it is not specified. But if it is given, you have to consider. So how much is the V? V is given as, how much is the V? So V is given as 240 volts. So V is given as 240 minus IA is given as 50 into RA is given as 0.1, this one. So into voltage drop across the brush is 2 brushes is 2 volts, so minus 2. So this gives the voltage drop or voltage left out in the armature, that what we call is back EMF, which is equal to 233 volts. You will get this as 233. Similarly, let us see for the next thing, that what is the next thing. So B is what they said, the power, the useful torque. Useful torque means this shaft torque is what the useful torque. So this torque we call as TSH, which is useful for our any kind of applications, useful for any applications, any apps. So this is what the useful torque. So how can we say that useful torque expression? So TSH is equal to the total output power or the net output power divided by omega. So total output power is what the mechanical power. So divided by 2 pi n is known. So n by 60. So it is given the output power is some 11.19 kilowatt. So 11.19. So kilowatt I'll add 10 power 3. So divided by 2 pi into speed is given as 1000. So divided by 60. So you simplify this. So let us see how much we get. So this is 106.85 Newton meter. The torque units are Newton meter. And I think I have not calculated required thing here. Just now you can put this EB over here. So you can get the torque TA directly. So EB is 233, IA is 50 amperes. So divided by 2 pi into speed is 1000. So divided by 60. So you simplify this expression. So how much is the torque is, so this torque value is something like triple 1.2 Newton meter. That what I got. Just yourself cross verify whether you are getting this or not. See that armature torque is more. So but the useful torque is a little less. Where does this torque is lost? It is lost in the form of frictional losses. In the form of frictional losses. See here, this is what the gross torque, but net torque is less than the gross torque. So there will be still certain losses which is frictional losses. So the left out torque is what the useful torque. This is useful torque. Okay. So now let us see the next point, that C. So what is C? C is the flux. So how can we, means where can we see the flux term? In the induced EMF. Can I write EB is equal to, so P Z by A, this is what the constant, into flux into the speed. Speed is given in RPM, so I'll use capital N divided by 60, or this entire term can be replaced by small n. Okay, this expression we've seen several times, just little modifications, other than that nothing is there. So now this EB is given as 233 and 4 pole machine. So the number of conductors is given as 540, and I said that for a wave connected winding the number of parallel paths is always 2. So this is 2, A is equal to 2. So since A is equal to 2 for wave winding, for wave winding, for wave winding. So next is the flux phi. So next is speed. This flux, what we need to determine, speed is 1000 rpm divided by 60. So you simplify and you will get this as milli, that is 12.94 milli Weber. This is what the flux per pole. Flux per pole. Similarly, let us see the next point, D. So what is the D? D is, so we need to find the rotational losses, right? So D is rotational losses. I already given how can we get this rotational losses? B minus C. What is B? Armature power. What is the C? Mechanical power. This is already given. 11.19 kilowatt is what this mechanical power. What I need to find is the armature power. How can I get the armature power? So armature voltage into armature current. So how much is the armature power? Let us see. PA is equal to EB into IA. How much is the EB? 233 into IA is how much? 50. So how much we get? So 230 into 50 is, so you will get this as 1,11650 watts. The same thing can also be found in another way. See how is this? So can I say the input power P in minus, so Ia square into Ra, that is what the armature copper losses, minus brush voltage drop into armature current which is passing through that brush contact resistance, is what the brush power loss. Brush brush loss, brush losses. So input minus these losses. So apart from this, what else is that? Right. So what does it give? PA. See here, let me show here. Let me show here this diagram. So this input V into I minus copper losses. If there are any brush contact losses, that losses also will be added in the copper loss only. Why? Because brush contact has resistance. That resistive losses all together called as copper losses only. Here brush losses also included. Brush losses. Now, once I subtract those losses, the left out power is what? The armature power. Let us see whether we get the same value or not. So, how much is the input power here? See, what is the input voltage? 240 volts. What is the input current? Armature current plus field current. That how much we got? 51 amperes. So, this is what the input. P in is this one. How much is the P in? V into I. How much is the V? 240 into current is 51. So how much we get? That is, so this is 51, some input power, minus Ia square into Ra. So Ia is 50 square into Ra is 0.1, minus Vb is 2 volts for 2 brushes into armature current is 50. Just cross verify this, you will get this as same as that of the Eb into Ia. This I already verified, just yourself cross check it. So you will get same value. So in either way, we can find the armature power, right? So once armature power is known, so can we find the rotational losses now? Rotational losses or stray losses or iron friction losses. Iron and friction losses is equal to this we said as, so B minus C. So what is B is armature power. What is C is output power. So these things already known. So armature power is 1650. Output power is 11 point, how much? 11.19 kilowatt. So triple one nine zero. 11.19 means triple one nine zero. So this is what the difference. So this difference is 460 watts. Just verify this. These are the rotational losses or sometimes called as stray losses. Now next is efficiency calculation. So this is which one? E, efficiency calculation. So how much is the efficiency? C by A. What is the C? Output. What is input? Pin. So if you know already output, directly substitute. Output is 11.19, that is 11190 divided by input is how much? Input we had just now calculated 240 into 51. 240 into 51 is what the input. How much we get is that, let me write here on the diagram. So this one is, so I got this as 12240 watts. So now output is known, input is known. So 12240. So this you will get as 0.9142. So if you want the percentage efficiency, so you can add this say as 91.42%. So like this, you can deal all the losses and efficiency concept in a DC motor. Usually, so we deal mostly with the shunt machines. So that's why I consider shunt example. Even if it is series motor, you can work on that. Just what change you see is that IA will become ISC, and there you need to carefully deal just from the equivalent circuit, and the remaining thing is circuit analysis concept only. Clear? So with this, let me stop here about the DC motor characteristics and efficiency calculations. In the next class we see some testing concepts. So okay, thank you.